In an effort to ensure proper adhesion between the sealant, glass, and spacer, it is necessary to verify that the proper sealant temperature is achieved per the sealant manufacturer's recommendations when the IGUs, or insulated glass units, are heated and pressed. There are several methods in which this may be done, but each has limitations. Common methods include temperature dots, thermocouple probes, and handheld IR temperature gauges, which will be described in this video. A kit K500-HMO-0002 containing these recommended items can be purchased through GED. Temperature dots are self-adhesive, surface mount labels, often having several dots which change color based upon the temperature of the surface being measured. This indirect method measures a glass surface and not the sealant temperature. These measurements may vary with different types of glass, coatings, glass thickness, and/or the condition of the oven's infrared emitters. This method can be used to correlate the actual sealant temperature when used in conjunction with a thermocouple probe. A thermocouple probe inserted directly into the sealant at the seal line as an IGU exits the oven and press provides the most accurate method of measuring the sealant temperature. This method, however, is a destructive test, and the IGUs tested using this method cannot be used for production as the seal has been compromised. It is therefore recommended that a correlation between the thermocouple readings and the temperature dots be established for each IGU's stack configuration. This is necessary as different types of glass, spacer, sealant, and desiccated matrix materials affect the amount of IR energy absorbed into the sealant from the oven emitters. The age, cleanliness, clarity, and types of emitters also has a great impact on the transmission of IR energy into the sealant. For this reason, the correlation should be verified every few months or when the emitters are replaced or the IG unit stack configuration has been changed. GED recommends that routine daily checks are performed using the temperature dots on the surface of the glass with the correlation values to verify that the proper sealant temperature is achieved. This measurement should be taken within 3 to 5 seconds after the unit exits the press. GED does not recommend the use of a handheld IR thermometer for qualifying seal line temperature. An IR gun is a thermometer which deduces the temperature from thermal radiation emitted by an object's surface. This indirect method of checking the seal line temperature often produces skewed data caused by reflective heat from the surface of the glass, consistency of the targeting and sensing area, and the surface emissivity sensitivity. This method does not directly measure the sealant temperature. Since using a thermocouple thermometer is measuring the actual sealant temperature, this is the best and most accurate method. However, since the thermocouple will damage the primary seal, this method must be conducted on test units rather than production units. This method is used to determine a correlation between the thermocouple probe data and that gathered by the temperature dots for each IG unit stack configuration. And then use of the temperature dots may be used for production evaluation, and the thermocouples may be used only as periodic quality verification in correlation to the temperature dots. Thermocouple thermometers come in a wide variety of models and options. GED part number 150-10870 is a recommended digital thermometer. Use of a thin leaf probe, like the GED part number 150-10871, which has a 2-inch long flat tip that can be inserted into the seal line, is best suited and provides better accuracy. The thermocouple and temperature dot placement should be consistent. Typically they are placed about 4 inches before the trailing corner of an IG as it exits the oven and press. This is making an assumption that the seal line temperature is consistent around the entire perimeter. Evidence of inconsistent temperature would be inconsistent IG unit thickness at the corners versus the midsections of the unit. This is often a result of running the conveyors too fast, not having enough emitters on, and/or having weak or broken emitters. Inconsistent heat issues need to be evaluated and corrected. The thermocouple should be inserted between the glass and the spacer, so just the tip of the probe is in the sealant. To make this task easier, the press height may be raised slightly so the IG unit doesn't get pressed completely. Keep in mind that less contact with the sealant to the glass may skew the readings slightly. Place a temperature dot on the bottom of the IGU and transfer the unit to the caster wheels at the end of the exit conveyor. Insert the probe between the bottom light and the spacer to ensure the oven is heating evenly top and bottom. Before collecting data to evaluate the correlation between the glass surface temperature and the seal line temperature, the condition of the oven should be evaluated. First, identify the type oven you are working with, as there are a variety of oven types available. Refer to the user guide that came with your machine to see what type you have. Some are just hot boxes that heat the IGU with ambient temperature. Others, like the GED 3500, 3550, and 3550 i3 ovens, operate primarily using infrared radiation. IR energy, which is not absorbed by the IGU, is transformed into convection heat. The emitters GED uses in these oven models operate at a set wavelength, which allows the infrared energy to pass through the glass and be absorbed directly into the sealant. The sealant then conducts heat back into the glass to assist with the adhesion process. A minimum oven temperature is required to assist in the convection heating of the glass, which aids in the adhesion process but is not the primary source of the heat input into the sealant. Increasing the oven chamber temperature over the factory settings will not significantly affect the seal line temperatures, but may lead to premature wear of the oven components. To effectively increase sealant temperatures, reduce the line speed or energize additional emitter banks if available. Note that any glass other than clear, non-tempered will reduce infrared transfer to the sealant and require a reduction in line speed and/or additional emitter banks to reach the same temperature as clear. A typical GED 35 series oven has two zones, left side and right side, and each zone has 3 banks. Typically, each bank has 4 emitters, 2 on the top and 2 on the bottom. The 3500 oven has bank control, allowing each bank to be turned on and off. The 3550 oven uses progressive bank control, which turns on and off emitters as the IG unit enters and exits each bank, saving energy. The GED 3550 i3 oven uses progressive bank control and offers preset modes that can automatically set the press height and line speed. This model also may be equipped with an option for individual emitter control. Examine the machine and look for any of the following issues and make repairs or adjustments as needed. Look for missing or damaged refractory. This can cause uneven or inadequate heating of an IGU. Look for broken, cloudy, or non-functioning emitters. This too can cause uneven and inadequate heating of an IG unit. Check for broken glass and debris in the oven. This can affect the efficiency of the emitters and can cause damage to the IGUs passing through. Verify that the fans and louvers are working properly. Non-functioning fans and louvers could cause excessive and uneven heating of the IGUs. Ensure that the conveyor, oven, and press are in plane and run at the same speed. Misalignment could cause lights to shift. Check the oven roll condition. Warped rolls can break or scratch IGUs and emitters and/or cause the glass to shift. Check the press roll condition. Build up or wear can cause uneven press out, lights to shift, contamination on the outside of the IGUs, and/or glass breakage. Verify the drive system and conveyors operate smoothly. Erratic operation could cause the lights to shift. Make sure all sensors are working properly and there are no machine faults. Ensure IGUs are being fed properly. Make sure the IGUs are tripping the proper sensors to turn on the appropriate emitters. For example, if the center sensor is tripped, both zones 1 and 2 will come on and overheat the unit, or if the outside sensors are not tripped, the applicable zone will not come on and the unit will not be heated enough. Also, if the units are not fed squarely, the sensor will detect the unit late and undetected early, which means the emitters will turn on late and turn off early and not properly heat the entire unit. Units should be fed squarely into the oven. By feeding the units this way, the emitters will turn on as the unit enters the oven and they'll turn off as it exits. Verify the units are heating evenly by checking the sealant temperature on the top and bottom of the IGUs. Also, check the overall thickness at the corners and the midsections of the IGUs for uneven press out due to uneven heat. Uneven heating may be due to emitters being clouded, rendering them inefficient. Bottom emitters in particular catch debris that enters the oven and falls from the IGUs, but are better protected if emitter shields are used. Also evaluate which emitters are on or off and make appropriate changes. Ensure that the emitters do not turn on or off too early or too late for an IGU entering or leaving the oven. Adjust the conveyor speed as needed. The objective of this procedure is to develop a table that will be posted by the oven that shows the correlation between the seal line temperature and the glass surface temperature for each IGU stack configuration, for the purpose of verifying that the seal line temperature is achieved in an effort to ensure good adhesion between the glass, spacer, and sealant. An example of this table can be found in GED document APN 0189. Periodically during the production day, the surface temperature should be checked to verify that the IGUs are getting hot enough to achieve proper seal line temperature. Use a data collecting sheet, also found in APN 0189. Run a test unit through the oven. If possible, do this with other production units so the oven is at normal operating temperature. As the unit exits, place a temperature dot over the spacer frame about 4 inches from the trailing end of the unit. Immediately insert the thermocouple probe into the seal line on the top side. Record both the temperature dot reading and the highest thermocouple reading. Repeat this process, measuring the surface temperature and the seal line temperature on the bottom of the unit. If necessary, quickly lift and transfer the unit to the non-driven rolls. If the units are triple pane, then each side of the center light should be checked as well. Using the manufacturer's recommended sealant temperature table in APN 0189, or recommendations from the manufacturer, was the proper seal line or resultant temperature achieved? Make appropriate adjustments to the conveyor speed and/or the emitter on-off configuration to achieve the proper seal line temperature. Document the correlating temperatures on the IG unit recipe table from the APN, along with the other required data like the stack configuration, press height, and conveyor speed. In this case, we had to turn a 160 temperature dot to achieve a recommended seal line temperature of approximately 180 degrees. The oven used here is new, so these values will change as the emitters wear. When the time comes that all the emitters have to be on, and the line speed has to be slowed down to where it negatively impacts the production throughput, then it will be necessary to replace the emitters or make other repairs to the oven. When replacing emitters, use only specially designed OEM emitters to ensure proper functionality. In addition to showing the manufacturer's recommended seal line or resultant temperature, the APN also provides suggested extruder and patch pump temperatures. The resultant temperature is typically slightly less than the suggested extruder temperature, as we want to soften the sealant for adhesion and pressing, but we don't want it to get too hot, which could result in overpressing the unit or shifted glass. The extruder temperature is a typical range that the material should be heated to in the extrusion process to provide good flow characteristics and proper adhesion to the spacer. The patch pump temperature is a recommended temperature that the sealant should be heated to for patching process over the assembly and gas holes on the finished IGU. This is considerably higher than the extrusion temperature because it not only has to bond well to the bare spacer, but it must heat the native sealant so that it creates an adequate adhesion with the existing material. Reference GED document ED0273, fourth corner patching procedure, or the video on fourth corner patching for more details on how to properly patch the fourth corner, assembly, and gas holes. Refer to the IG unit model in the APN. You want to ensure that the press height is correct in order to verify the proper wet-out dimensions. Measure the overall IG unit thickness and subtract from that the glass thickness and the actual spacer width. Divide what is left by 2 to determine the theoretical sealant thickness on each side. This should be a minimum of 15 to 25 thousandths. If necessary, adjust the press height until these dimensions are met. This measurement is theoretical because uneven heat from top to bottom may result in different wet-out characteristics. Another method discussed in the APN is to wrap a piece of tape around the spacer, run it through the extruder, and remove the tape before stacking the IG unit. This will leave a bare metal area on each side of the spacer, where a feeler gauge may be used to determine the actual wet-out thickness. Note, if the wet-out thickness and width cannot be achieved, it may be necessary to adjust the application at the extruder. Develop this correlation for each stack configuration. Create a table with each configuration and its respective press height, conveyor speed, emitter configuration, and target temperature dot, and then post the table at the oven.